So good morning, everyone. My name is Pengcheng Yao. I'm a PhD candidate from Huazhong University of Science and Technology. It's my great honor to be here to share our recent work. And thanks a lot for the invitation from Professor He. So in the next 30 minutes, I will represent Professor Zheng to share our recent researches on high-performance graph analytics accelerator. This is the outline of this talk. And I will first introduce the background of graph analytics and then provide the introduction of our work. And at the end, I will also give a short conclusion of this talk. Okay, so let's begin with the background of the graph analytics. So many of you may have a lot of questions on this topic. So the first major question may be, what is graph? Graph is a concept from graph theory, which is developed from the well-known cyberbridge of the Königsberg problem. So people want to know how to walk across each bridge shown in this picture once and only once. So while the problem description is quite simple, it is hard to deal with by using the traditional mathematical theories. So to solve the problem, Euler, who is a famous mathematician, proposes a new data structure that's to say graph to describe the relationships between different entities. So a graph consists of vertices and edges, where a vertex often represents an entity and an edge represents a relationship. So for example, as shown in this picture, by abstracting the raster area to vertices and bridges to edges, the original data can be concisely represented by an undirected graph. So because of its powerful abstraction, graph data is ubiquitous in our life. So for example, World Wide Web, social networks, traffic networks, and biologists. So with the above introduction, we may know that graph is a data structure consists of vertices and edges. But what is graph analytics? So in the recent years, the generality of graph attracts a lot of contention. Therefore, many researchers has been proposed to solve real-world problems by analyzing the graphs, so which we call graph analytics. Graph analytics can be generally divided into two categories, including graph processing and graph mining. And so thanks a lot for the introduction, for the speech of Xinyu. So I have not to introduce the GIS model in detail. So for graph processing, it computes vertex and edge properties to analyze a graph like BFS, SSSP, and PageRank. More specifically, each vertex interactively updates itself based on the property of its neighbors with the GIS model. So graph processing is widely used in our life. For example, we can use it to model how people interact and influence each other to predict COVID-19 outbreaks. So another aspect of graph analytics is graph mining. For graph mining, it searches interesting subgraphs to analyze graph structures like subgraph matching, motif counting, and frequent subgraph mining. So more specifically, each subgraph interactively adds one neighboring vertex to the self to find the matches of the required pattern. And it generally follows an extend, filter, and process model, which is similar to the GIS model used in the graph processing. In the extend stage, each subgraph adds one of its neighboring vertex to generate a new candidate graph. And the new candidate graph is one larger than the existing subgraph. And then in the filter stage, the new subgraph is filtered by user-defined function. For example, in subgraph matching, the algorithm will match the new subgraph to the user required subgraph to find if they are matching. So finally, in the process stage, the new subgraph is processed to get a result. Like we calculate the occurrence of specific graph structure in motif counting. Similar to graph processing, graph mining is also widely used in social network, finance, and biology. For example, we can use it to detect the suspicious accounts by searching specific cash flow. So as is known to all, we are in a golden age of AI. Machine learning technologies are ubiquitous in our life. In software, machine learning is adopted in NLP image processing, autopilot, and IoT. And in hardware, machine learning is also used in ASIC designs, EDA tools. So therefore, direct question is why we need to research graph analytics, which seems to be out of date. So we think that the answer lies in the need of processing sparse data in real-world applications. In general, both of machine learning and graph analytics can be abstracted as matrix computation. So as this figure shows, machine learning performs dense matrix computation where most of the elements are non-zero. And different from that, graph analytics performs sparse matrix computation where most of the elements are zero. So for example, more than 99% of the elements in Twitter graph are zero, which does not need to be actually processed. Because of the differences in sparsity, machine learning and graph analytics are skilled at different areas. Graph mining is more efficient for regular applications, while the graph mining is more efficient for irregular ones. And both of them are necessary for solving the real-world problem. We can see that machine learning may skill at NLP and image processing, while the graph analytics may skill at social network analysis and RDF database. This is the first reason, and more importantly, researches on sparsity are essential for our lives. So first of all, sparsity is ubiquitous in our life. For example, we only interact with a limited number of items, resulting in natural sparse relationships. And moreover, even typical dense applications might have some kinds of sparsity. So for example, machine learning technologies like sparse neural networks and graph neural networks also have to process the sparse data. And however, most of the existing softwares and hardwares are designed for dense data, leading to suboptimal performance when processing the sparse data. So this is a more detailed example of the inefficiencies when processing the irregular data. So sparse data, when processing sparse data, it may lead to the irregular computation and the irregular memory accesses. In the left picture, we can observe that the graph analytics and the graph machine learning have a significant differences. So when processing the sparse data, the data flow is significantly randomized, which can be hardly predicted in the compounding time. So therefore, as shown in the right picture, when we implement graph analytics in general purpose architecture, it will lead to severe data contentions because different pipelines or we say different cores might access the same data in the same time. So in addition, for memory subsystem, the random access leads to bad time and spatial locality, resulting in extremely low memory performance. So as a conclusion, there is an increasing demand to redesign the hardware architecture to efficiently process the irregular applications like graph analytics. So in the next, I will introduce our work on the graph accelerator. Our objective is to build a general purpose graph analytics computer. This is also a project funded by National Kids Research and Development Program of China. So in the next slides, I will mainly introduce our research effort on accelerator designs, including architecture performance analysis, computation architecture, and the memory subsystem. The related paper are accepted by CTSIS, PACT, and Micro. While our objective is to design the specialized accelerator for graph analytics, the first step is to understand its actual performance bottleneck. And existing work always believes that graph analytics is only bottlenecked by memory access. However, from our detailed experiments on typical algorithms and graph systems, we find that graph analytics is both memory and computation intensive. So from this table, we can see that although there are 40% of the CPU cycles are stored on memory access, there are also about 35% of the CPU cycles are stored on the core execution. So to have a deep understanding of the core efficiency, we'll analyze the core execution of the graph and the traditional SPAC application. In general, the average instruction per cycle of graph applications is only half of that of the SPAC application. The reason lies, we think that the reason lies in the low instruction level parallelism of graph applications. For SPAC, only 33% of CPU cycles runs in low IRP of 0 or 1. And however, for graph applications, such number reaches 60%, which is about twice of the, as large as twice of the SPAC applications. This low instruction level parallelism is because of the limitation of out-of-core execution in existing CPUs. So more specifically, although existing CPU supports out-of-order execution, it follows the sequential requirement. That is, although the instruction can be executed differently from the programming order, they have to finish every instruction as same as the programming order to ensure the correctness. So therefore, when facing a long latency instructions like the load instruction shown in the left picture, the out-of-execution buffers can be soon be clogged by the succeeding instructions that are already being executed. So from our experiment, the out-of-order buffer accounts for about 50% of the total resource-related stores. So therefore, in order to achieve the considerable performance, the performance of long latency instructions of graph analytics must be improved. In general, there are about two different kinds of long latency instructions in graph analytics. So first of all is the computation instructions of including the atomic operations, and then another one is memory instructions that graph analytics may perform a lot of random memory access. So if you are interested in this work, you can find more details in our SDSS paper. So our next two works are mainly deal with these two kind of long latency instructions. So for the first one, the atomic operations, we propose a specialized computation architecture for graph analytics. For regular application, the workloads can be evenly partitioned to different pipelines. And with that, if every data is only accessed by one pipeline in each cycle, as this picture shows, the traditional these workloads can be efficiently processed by typical hardware designs like the syntonic way. However, for graph analytics, no matter how we partition the workloads, every data must still be simultaneously accessed by multiple pipelines because of the irregular data dependency. So to solve the problem, existing researchers use CAM-like structure to atomically process the access of the conflict data. While these designs ensure the correctness of computation results, they lead to severe overhead on atomic operations. As shown in the left picture, the accelerator receives full access requests on vertex 1 in the first cycle, and in order to ensure the atomicity, the accelerator only processes the first request and blocks all other requests of the vertex 1 in the first cycle. So as a result, the process of requests on vertex 1 is sequentialized, and because of this result, the pipeline frequently stored and consumes 4 more cycles compared to the idle situation. From our experiment, atomic operations account for about 45% overhead for different algorithms and the data set. So therefore, an intuitive question is whether we can parallelize the process of conflict data while ensuring the accuracy of results. So through the deep analysis, we find that graph atomic operations always follow commutative law and associative law. That is, no matter how we change the execution order, and the correctness of the final result will not be broken. So based on this observation, we propose our parallel accumulation in size. So more specifically, as shown in the right picture, we accumulate the atomic operations in parallel before writing back the final results. While this insight sounds to be promising because we can achieve that idle performance and achieve fully pipeline processing, it is not easy to efficiently implement this insight. This is because the challenge lies in the irregular vertex degrees. In an input graph, different vertices have different number of degrees, so that the data received in each cycle might belong to multiple vertices. So, however, as shown in the left picture, traditional idle trees can only accumulate the data for one vertex, leading to suboptimal performance. For example, in the right picture, we can see that the accelerator received 2 requests on vertex 1 and 2 requests on vertex 2 in the first cycle. And because of the accumulator can only accumulate one vertex, the requests on vertex 2 are blocked and finally consumes 2 more cycles. So for this challenge, an intuitive design is to using multiple idle trees. For example, if we assume that we might receive at least 6 or 8 receive 8 vertices in each cycle, we might implement 8 other trees in our hardware. While this mechanism can deal with our problem, but it is kind of a cop-out. It works, but it might significantly increase the hardware fan-outs and finally decrease the overall performance. So to efficiently support multiple vertices accumulation, we make detailed problem formulation. The original problem is an integer programming, which is hard to be dealt with. Fortunately, we find a special partition order in the poor model of graph processing. That is, all requests are sent in an ascending order of the destination vertex. With this partition order, the problem can be simplified into a modified prefix sum problem. So the only difference is between our problem and the traditional prefix sum problem is that we have a breakpoint and the filter in our situation. So the breakpoint exists because that we only sum its related data for each vertex. We do not sum the vertex of other data for each vertex. And the filter is because that each vertex only needs the final accumulated result. We do not need, for example, if it has 3 data, we do not need the result of accumulate the first 2 data. So based on this formalization, we propose our accumulator based on the traditional prefix sum iders. So in general, all prefix sum iders can be used for our design. We finally choose lambda Fisher iders for the minimize latency and resources. So for breakpoint, we add some bits to each data as its vertex ID. With this vertex ID, the simplified problem can be easily done by so with the vertex ID breakpoint can be easily found by comparing the IDs of consecutive data. So for specific hardware design, we replace the idle logic with the idle logic in the idle tree with the conditional idle logic to achieve dynamic breakpoint recognition. As this shows, when an idle receives 2 inputs, it first checks the IDs of these 2 inputs. If their IDs are the same, it directly adds them and outputs the results. Otherwise, it will directly output the second result. So for the data filtering, we directly select the accumulated result in the location of each vertex last data. So that this might be a little complex, so I will show you simple example of our accumulation workflow. So so we can see that our accumulator is fully pipelined. So in the first cycle, it receives 8 updates in the first cycle, and we can see these 8 updates belongs to 3 different vertices, and each update is represented by a tuple of value and vertex ID. And in the second and third cycle, the either in the red block directly send the second data that you see the data of vertex 2. Because of the IDs of the 2 inputs, this 2, 1 are different. And for the IDs are same, for example, for the first update and the second date, the IDers will directly add them and send for the further execution. So at the last, because of the location of the last update of vertex 1 is 3, the accumulator selects the data in the third port as a valid result for the vertex 1. To demonstrate the effectiveness of the designs, we conduct experiment on Xilinx acceleration card, and we only use 2-channel memories. I need to mention that this result is an improved one, so it might be higher than what we reported in our paper. So our accelerator achieves at most 5 G types for BFS and 4 G types of page rank, which is more than 3 times speed up, speed up comparing to the state-of-the-art full graph. For the finance anti-fraud applications, our accelerator also achieves about 4 times speed up comparing to the CPU baseline. Okay, so this is all of our designs to deal with the first types of long latency instruction. So while the above design deal with the computation bottleneck, there is still bottleneck in memory accesses. So for graph processing, it mainly performs random access on vertex data. So considering that the vertex data is often as small as tens of megabytes, existing accelerators statically hold all vertex data on chip to achieve costly off-chip memory. For example, we can statically load all vertex data in the VRAM of FPGA and do not replace it at the runtime. So we can see that with this mechanism, all the random accesses will finally access the data on chip, and so to largely improve the memory access performance. While this mechanism is efficient for graph processing, it's not for graph mining, which performs random accesses on both vertex and edge data. But in general, edge data is always larger than vertex data by several orders of magnitude. It's not practical to hold all edge data for graph mining with unlimited on-chip memory capacity. So since it's not impossible, it is impossible to store all irregular data on chip. Our intuition is whether we can store only a small portion of data to achieve considerable performance. So the answer for this is yes. The exploration locality in graph mining makes this aggressive intuition to be possible. So the real-world graphs always follow a power law degree distribution, where a small number of vertices connects with many edges. And during the process of graph mining, as the size of subgraphs increases during the process, high-degree vertex is more likely to be added in the subgraph compared to the low-degree vertex. So therefore, the power law distribution in natural graphs is significantly amplified during the process. So for example, in the top picture, you can see that vertex 8 is only included in 3 subgraphs in the first iteration, but quickly 9 subgraphs in the second iteration. So from our experimental results, about 5% vertex and edge data can generate at most 95% memory accesses. So based on these insights, we propose a divide and conquer methodology to that we statically retain the frequent access data and dynamically replace the left data. So however, while this methodology is simple, it is still challenging to implement our insight. So first of all, it is extremely hard to precisely locate the frequently accessed data. A low-degree vertex which is connected with many high-degree vertices might also be frequently accessed. And second, the intermediate data in graph mining can be as large as terabytes, which is even hard to be stored in the off-chip memory. So for the first challenge, we propose a novel memory hierarchy consists of a scratchpad memory and cache. The frequently accessed data is held in scratchpad memory, as live data is dynamically replaced in cache. So for each graph data, we find that its access frequency is mainly determined by the degree of itself and its one-hop neighbors. So this is because of the power law distribution, the edges of high-degree vertices and their direct neighbors account for almost all edges of the graph. Therefore, the degrees of the other neighbors contribute little to the access frequency. Also from our experiment result, we can see that the access frequency based on the one-hop neighbor can result at most, we can say at most nearly the 99% of accuracy. And if we enlarge the scale, that's to see if we use 2 hops or 3 hops or even larger hops neighbors degree, the accuracies do not significantly increases. So based on this observation, we also propose a specialized data addressing mechanism and replacement policy to predict the access frequency of each data with high accuracy and low overhead at runtime. And because of the time limitation, and can now introduce our design in more details. So if you are interested in our work, you can find more details in our paper. So besides the memory designs for the second challenge, we also propose some specialized architecture designs. And so we can also conduct experiments on the Zenith acceleration card. Comparing to the state-of-the-art CPU-based graph mining system, we can achieve at least 2 times speed up and at least 33 times more energy efficiency. So this is the conclusion of this talk. So the first one is that the graph is ubiquitous in our life, and then the researching graph analytics is important. And the left is the 3 insights of our work. So the first insight is that graph processing is bottlenecked by both computation and memory access. And atomic operation. The second one is atomic operations in graph analytics can be accumulated in parallel to avoid pipeline stores. And the third one is that exploration locality can be leveraged to achieve considerable memory performance on large volume of graph data. So yes, that's all of our work. So thanks a lot. And